So thank you very much, all of you, for joining. My name is Louise Bierregaard, and I'm a senior research engineer here at the CTS Ferroperm Piezoceramics. And this is our Innovation Hub webinar series, the spring installment. I'll take you through the webinar slides. So this is how it looks. So we have 4 webinars in this spring, and we'll present them a bit more at the end. First, I would like to tell you a little bit about our Innovation Hub initiative. So a lot of things start with an idea, and ideas can come from many places. It could be your own idea, an internal idea. It could be maybe idea coming from this webinar. And then after having an idea, it can be a good idea to have an initial evaluation of the idea. And here we have some free services that could be free sample, FE modeling, and we also offer characterizations or small feasibility studies. After this, an idea can move to the proof of concept stage, and here we have the customer ordered projects where we can help with product design, prototype manufacturing, performance evaluation, or cost evaluation. And then from the proof of concept, it can move to the pilot production, full-scale production, and entering the market. And to elaborate a bit on the free services that we offer, we have a characterization service where we offer a full spectrum of measurements and characterization of your material or device, also in a wide temperature range. We have workshop webinars and trainings, such as this webinar, and we also offer some modeling services. And then finally, free samples, where we can provide you with a wide variety of samples of different types and materials, also including our thick film and polymer-based composites. And under the next stage, the customer ordered projects in the Innovation Hub, we can help you with the design of your product for a particular application, to evaluate the performance of your device, or manufacture the first prototypes for proof of concept. And under this, we offer to share 50% of the cost to show our commitment. So new ideas may require completely different and customized solutions, and we can try to help you with that. So this was a bit about our Innovation Hub initiatives. And if you have any questions or inquiries, you're very welcome to contact us. And finally, we move on to today's webinar, which is the determination and use of the piezoelectric matrix. And it will be presented by Dr. Erling Ringgaard, which is our principal material scientist here at CTS Ferroperm Piezoceramics, with more than 25 years of experience within the piezoelectric ceramics field. And on the modeling side, we have Dr. Nikolaj Feidenhans'l, who is our senior project manager and has been working on most of our modeling projects for more than 5 years. So with that, I would we should start with the webinar. So over to you, Erling. I should say that if you have any questions during the webinar, you're very welcome to post it. And I'll keep an eye on both the chat and the Q&A function.
Thank you, Louise. And I will hurry up and start. So good afternoon, everybody. So I'm Erling Ringgaard, as Louise said. So I'll show you an outline of the talk. I'll start with a brief introduction, just recalling the piezoelectric coefficients and how we number them. And then I'll be talking a bit about how to determine these coefficients, at least two different ways. And then I'll touch upon some parameters that affect the piezoelectric properties, and I'll sum up in the end. So just to recall, this is a slide I've shown in a previous webinar, recalling the piezoelectric effect. You can see that if we just take a plate which is electroded and poled in a standard way, then if we have an input force, we can find the stress, and from that we can find the generated electric field by the direct piezoelectric effect. And for that we need a coefficient. So in this case it's a G coefficient. And now we actually need to agree on how we really keep track of the directions. So we use this rectangular coordinate system with a 1, 2, and 3 axes, which are the X, Y, and Z axes. And you'll notice we also have some additional numbers, 4, 5, and 6, which designate shear around the 1, 2, and 3 axis. And as described here, you use the first index as the electrical index, so it can be 1, 2, and 3. And the second index, the P index, can, as I said, be 1 to 6. And it's very important to notice that the 3 axis is then defined as the poling direction. Now, similar, you have the converse effect, and it works in exactly the same way. And I should just give one example here that, again, if you have the input electric field, then you can find the strain. And now you use not the G coefficient, but the D coefficient. But otherwise, things are the same. And these are linear effects. So I put 2 more equations now so that you can see that the D and G coefficients, they appear both for the direct and converse effects. It's just a matter of which input and output parameters you choose. And finally, on this slide, I'll mention that the coupling coefficients are relevant at resonance. And for those, we also use the same indices, the electrical and the mechanical index. Okay, and I'll just elaborate a little more on these linear piezoelectric equation of state. So I'll go through quickly. I also showed this before. So for the isotropic case, you have something which is not piezoelectric. So you have pretty simple equations of state describing the mechanical and electrical case. You can find the strain from the stress here, and you can find dielectric displacement from the electric field. So if I move quickly to the piezoelectric case, you'll see that in addition to the standard elastic contribution here, you have the piezoelectric contribution where you have an input parameter which is electric. And for the electrical case, you have an additional term here which has an input of mechanical stress. So just moving on and elaborating further, you can say that you actually can combine the inputs of both stress and electric field in a vector here. And from that, you can find another vector, which is basically the whole strain matrix and the dielectric displacement matrix. And in order to find that, you need a large combined matrix, which is consisting of the mechanical properties here, and then piezoelectric properties, in this case, D coefficient, and then dielectric properties here. I'll show you how this may look in a moment. I'll just mention that this is just one case where you have these 2 input parameters, stress and electric field, and output parameters, strain and dielectric displacement. But you can actually imagine other combinations. If you have a strain and electric field as input, you can find these 2 other outputs, and then you need a different matrix where you now have, for example, the stiffness matrix instead of the compliance matrix. And just for completeness, I'll show the 2 other versions, but I'll not have time to go into detail. But here you have the G coefficient and the H coefficient, 2 other piezoelectric coefficients. And now looking at how this may look, we should first recognize that a piezoelectric material has a symmetry of a cone, so it reduces the number of different parameters. So in consequence, you can see that there are a lot of zeros here, and some of the parameters are actually identical, like you see with the 1, 3 here. And in total, we need 10 different parameters, 5 in the mechanical matrix, 3 in the piezoelectric, and 2 in the dielectric matrix. I'll also mention that there are also losses involved, and just very briefly, I can mention that you can define them generally as, for example, the dielectric loss, which is quite well known from basically from a complex permittivity. You can also define mechanical losses, normally using the quality factor, mechanical quality factor, and finally you can even introduce piezoelectric losses.
So Erling, we have a question.
Yes.
So Kaiser is asking, are these properties easy to measure?
Well, I wouldn't say easy, but they can all be measured, and I'll actually show in some of the next slides how you can measure them from impedance spectrums. So I'll be happy to answer further questions, but probably it's a good timing just to show 2 ways now how to measure these properties. So let me just introduce the standards that we are using. So there's a very well-known IEEE ANSI standard from 1987. It's no longer in force, but it's still a good reference work. Not that straightforward to use. For normal use, I would maybe recommend this European standard, which is not as detailed as the other one, but it's specifically aimed at piezoceramics, not so much on quartz crystals as in the other one. And the nice thing is that it has a very methodical approach to the full characterization. Okay, so let me first just recall what do I mean by an impedance spectrum. So by this I mean that we measure the impedance, the electrical impedance, as a function of frequency. And if you have a piezoelectric material, you will find a resonance, typically more resonances, and they are defined by basically a minimum in impedance and a maximum. And there are 3 very closely related frequencies close to the minimum, and similar 3 closely related resonance frequencies at the maximum here. So today I'll just be mentioning this as resonance frequency and this as anti-resonance frequency. Okay, and if you plot the impedance in a logarithmic plot, you see this very characteristic behavior that it has a clearly visible minimum and a similar maximum here. And if you take a broader frequency spectrum, you'll see for example, for a disk, a planar resonance and a thickness resonance. Okay, so now actually we are close to an answer to the question. How can you measure these properties? Well, this is taken from this European standard that I mentioned. So this standard describes 5 standard geometries, and then according to this scheme, you can actually look up some equation numbers, and then you can actually go through one by one, and then you get numbers out in the end. So I'll take one example. I'll look at a pretty straightforward one, a long cylinder, a long bar resonating in the longitudinal length mode. So for this, you see the polling direction like this, and the vibration direction also marked by the black arrow. So according to the standard, we should start with equation 43, and it looks like this. You need the 2 frequencies that I mentioned. Here it's designated Fs and Fp, resonance and anti-resonance. You put them into the equation, and then you get the K3 coupling coefficient out. Next, it says go to equation 17. And this equation 17 needs the density as input, the length of this cylinder, and also anti-resonance frequency. And from this, you find one of the mechanical parameters, the S33 compliance with a superscript D, meaning at open conditions, standard or constant dielectric displacement. What next? Well, then you can go to the other S33, the short one, at standard electric field, and using the K33 coefficient, you can find this one from the other compliance. What next? Well, you in order to find D33, you also need the permittivity in the 3 direction. And this is a very standard. I think many of you know how this can be found directly from the capacitance and the dimensions. So I didn't include that equation. And finally, with these numbers, with the K33 and the permittivity and the S33 compliance, you can find the D33 coefficient. And that's really the first part of putting into this matrix and using similar equations and similar measurements on the other geometries. You actually are able to find all parameters. Now I'll show something about I would say a more advanced method. We call it the Alemany method. It was developed by a researcher from a Spanish group in Madrid, Carlos Alemany, as referenced here. So the idea here is you can get more detailed measurements, and you can even get complex coefficients, meaning that you would directly measure the losses directly from the impedance spectrum. So here we need at least 3 samples, not 5, but in principle you can do with 3 samples. The first one that I mentioned already, the long cylinder. The next one would be a thin disk, which would give 2 resonances, the planar resonance and the thickness resonance. And then finally, you need 1 sample describing the shear properties. So here you see a standard shear pole part where you see the 3 number indicating the poling direction here, and these 2 arrows indicating the shear displacement. Actually, more recently, the Spanish group have introduced a different geometry, which is poled in the thickness direction, and this one turns out to give more pure resonances. Okay, just finally, before I leave this, I'll mention that the method actually uses, let's say, an impedance spectrum of a pure resonance, and then it's really trying to adapt all the coefficients to get a very good match with the peaks in this spectrum. This spectrum looks a little different. It's actually a peak in conductance and a peak in resistance, but it comes directly from the impedance spectrum. It's similar here. You see what is called the susceptance and the reactance, which are the imaginary parts of the admittance and the impedance. But anyway, all these come out of the impedance spectrum. Okay, let me move on. So as we also promised in the introduction to this webinar, we'll also touch a little upon how to measure what actually affect these properties. So there are several numbers that affect the properties of several parameters. There's time, as described by aging coefficients. There's also the mechanical stress that we subject the material to, and it can be like a dynamical stress, and it can also be a static stress. And similar for the electric field, an AC field or a DC bias. And finally, there's a frequency dependence. I'll give some examples in the end about temperature if I have time. So I'll just quickly mention some references for the mechanical stress and electrical field and frequency dependence by these authors. Okay, and this is an example of a part of such a complex data set for our soft PZT, where you have all the numbers as complex numbers. Here are some measurements that we did ourselves on a lead-free KNN material. Some numbers are missing because we didn't have the long cylindrical rod at that point. I think I will move forward so that I'll leave some time for Nikolaj. Here we have examples of how the permittivity changes with the temperature, where you see the Curie point here, and you see some inference of the frequency, as I mentioned before. I'll also mention how the temperature will affect the impedance spectra. The green one is at 25 degrees, and the yellow one is at 250 degrees, where you see how the impedance spectra are actually changing with temperatures. So if we made such measurements on all these 9 temperatures that we measured at that time, we could actually get 9 data sets describing the full properties of these 9 temperatures. But this is quite an extensive work. There are some details about how the impedance spectra evolved, but I'll also maybe skip that for now. I don't have that much time left. So I think I will conclude now by saying that I showed you how the basic piezoelectric matrix, as I call it, consists of at least 10 independent coefficients. I mentioned those before: mechanical, dielectric, and piezoelectric. I showed how we can determine them by analyzing these impedance spectra, by choosing suitable shapes and dimensions. And at least 3 shapes are needed. It could also be more, but at least a thin disk and a long rod and a shear plate. And finally, I mentioned some parameters affecting these coefficients. Okay, I will now give the floor to Nikolaj, and if there are some further questions, we can take them in the end. Okay.
Yes, so thank you, Erling. Then I will continue on some modeling, where we then will use those material properties Erling just described. So the main part of my presentation will be showing an actual model and how to then apply the material properties and what you can do with the finite element modeling, and how to which factors to consider when you set up such a model. But to begin with, I just want to give some very quick background on FEM modeling. So, so general concept of FEM modeling is that you can put approximate solutions to complex systems that are then too complex for analytical solutions. So one example could be if you have a very simple straight beam, a cantilever, then you have it fixed at one end and you apply force. That's what I've shown here in the sketch to the right. Then you can actually analytically calculate exactly how it will bend and what stresses you will have throughout this beam. And this is a very simple model, and obviously you can do the same analysis using finite element modeling. You build it down here, apply a force to the end, and you see how it bends. And those two should be very similar. But often we have more complex systems than this, and then it's simply impossible to get analytical solutions. But instead, we can then use modeling to get these approximate solutions. And by approximate, it means mainly, how precisely you have defined your, for example, material properties, and also how small regions you divide your element into. Because for modeling, you then divide your part into a lot of small regions called mesh elements. It's the triangles you see down here in gray in the FEM model. And then you set up all the physical equations describing your systems in a matrix, where in each point of these mesh elements, they are then coupled together, and then obviously in the end, they're coupled to your boundary conditions. And by this, you can then solve how the whole system would behave. And a good thing about modeling is that you can also couple different physics. So you can have heating based on mechanical vibrations or electrical currents, for example. And also importantly for this kind of modeling is that you need to imply symmetries so they can reduce your model size. Otherwise, it often gets too big to actually solve realistically. And the main features, or the simplest features you need for a model is to have some geometry you want to analyze. You need your material parameters to describe your system. And then you obviously need to also state what kind of physics you want to analyze, what equations describe these effects, and also some boundary conditions for defining the model. Then you need your mesh, how finally you want to divide your geometry into small elements, and then some solver to actually do all the calculations. Luckily, most of this is taken care of by commercial softwares. So at our site, we mainly use the COMSOL multi-physics software, but other sites within the CTS corporation, they use other FEM modeling software. So we have combined a small table here illustrating some of the differences between these softwares. Because as soon as you start getting into modeling, you would quite quickly realizing you get kind of locked into whatever software you're using, because you start to have so many models and knowing about how to set things up. So it can easily become quite a time-consuming task if you want to change software, and you might not. So we prefer not changing your FEM software too often. So this shows some quick comparison of some of the main things. I won't go through all of them, but some of the main features I think is you need to look for which kind of domain you want to solve in. If it's frequency space or time, you have like impulse responses, or if you look at more like static or continuous vibrations. Then there's obviously generally how complex things your software can do, setting up different geometries, rotated things, couplings to other parts, and also different physical domains like acoustics and heating and stuff. And then two other features that you might not consider is then actually the customer support is often very helpful when you have issues with your model, that you can actually reach out to the company and get in contact directly with some of the application engineers and get their input on how to set up your model or what's wrong with your model. And also if they have a lot of like demos or tutorials. And then obviously kind of the business case for the simulation software. Some of them are classically yearly licenses where you then do the simulations on your local PC. That's what we have, but obviously this constitutes a quite large entry barrier. You could say that you need to pay quite big fee up front. It's in the tens of thousands of euros at least. While others, for example, OnScale, they do this pay per hour on their cloud computer. So that's very easy to start simulating. But then again, as I mentioned to begin with, you should take care not to get locked into the software that's wrong for your needs in the end, if you then cannot do the complex things you would like later on, for example. Yeah, so I think that was it for the introduction and different softwares. Then I want to show some models I made in COMSOL multiphysics, and then through these describe the different factors and how I set them up. So I'm gonna show a model of a simple HIFU transducer, so high intensity focused ultrasound transducer. These are used in the medical industry for treatment. So for example, typically burning cancer underneath the skin so doing kind of surgery without having to physically like open through the skin. So they can focus the ultrasound in a small region above the piezo, and they can generate temperatures that's so high that the tissue will actually die in there. The model, this is the 3D model. You see the kind of like the curved shape, and then there's a hole in the center for an imaging element that's often used to monitor how much tissue you damage. But we're going to do the model not in 3D, but in axial symmetry. So what you will see when I show it is this kind of cross section. So half the shape in one cross section, and then it's being rotated around this symmetry axis. I have 3 different versions: a freestanding, which is the part we will then typically produce, and then you will use it to couple into water and have your focusing in there. And then lastly, we can mount a holder and see how that affects it all. So I will just change to software here. Okay, so then this is the interface for COMSOL multiphysics. Here for example, here we have the 3D shape I showed you, and then the geometry we actually model is only this half cross section. So what I would typically do with building such model is to define most of the geometry and parameters as variables, so then you can quite easily go in and change it afterwards, and you can have them linked together. For example, defining the mesh size based upon the frequency you use, stuff like that. So you get a more adaptive model. So when I mentioned these basic things you needed for the model, so that's the geometry we defined in here. You see it, it's different, of course, different software, how you define it, or if you load in a CAD model. This one I draw some circles and made this lens shape. Then we have the materials. So I choose PZ26, one of our standard hard ceramics. We have typed in all our different materials. Obviously, this takes some time, but once you have done it, you have them available. And then, as Erling mentioned, you have these different equation systems, whether they are from strain or stress related based. Those you can define. For most software, it wouldn't matter which you define because they can be calculated from each other. So that's kind of built in. But then we would input all the material properties as Erling showcased. So this is then the compliance matrix, and you see the different elements in this matrix, the symmetries. Here they are defined as variables because then we can have the values defined down here and then link them up there. But yeah, then this material governs this region. Then next you have the physics. So for piezo, you need some mechanical and the electrical to couple between the piezoelectric effect. And for the mechanical, for a freestanding transducer, it's typically just a basic setup. And you define it then as a piezoelectric material, so it knows which equation to use. And then, most importantly, you need to have the right coordinate system. As Erling said, all the material parameters are defined relatively to the Poling axis. And for a flat disk or something, it's quite simple because then you can just use the normal XY coordinate system and have all, for example, along the Z direction. But if you start to have elements that are rotated 90 degrees or this kind of focused element, then you need to put in the right coordinate system, actually. And I'll have this curvilinear system I will show you later. And then also damping is very important to apply to a model, because without damping, you'll get infinitely sharp resonances. And also then very high intensities when you start coupling into border. What we normally apply is an isotropic loss factor. So that's given directly from the Q value. So it's mechanical damping based on the Q value. And it just corresponds to losing some energy in each oscillation cycle. And as Alex mentioned, if you start determining the complex parameters, you can use these complex terms to then define the losses. But then it's a whole, you need to know all the complex material parameters. For the electrostatics, just define your ground and then your terminal, apply some fixed voltage. Then we have this curvilinear coordinate system I told you. So it's kind of like what it actually is. I don't know, it might be specific to COMSOL or other software might have the same methods. But generally what it does is that you can actually calculate kind of like approximate like field lines between the two surfaces. So we have an inlet and an outlet. And then, so how would field lines or water flow then go between these two surfaces? So then you kind of model how the polling will be in reality. I will show the coordinate system later on. Then obviously multi-physics, we need a coupling between the mechanical and the electrical domain. So this is governed by this software here. And then we have the mesh, as I told you, dividing the our part into a lot of small features so that you can then calculate, solve all these equations. But just this shape is quite simple. But then I want to just mention that you should consider how small you need it, because this will affect your simulation time. And typically, and because also the mesh size would also depend on what kind of frequencies you're looking at, because higher frequencies means shorter wavelengths in your structure, and need to resolve them accurately. And you should generally have around 12 nodes per wavelength. So for what's it called, this kind of second order element, you should have 5 mesh elements per wavelength. But we can show that when we have run through the simulation. Then, so that's kind of like setting up the model. Then we do the actual solving. So we do the frequency domain, this model. So that would be similar to having like continuously, having a piezo excited by a continuous sine wave, and you have standing waves. So then you define a range of frequencies where you then would like to solve the model. So let me show the results. So from this, we can then get the impedance spectrum. So this is the full spectrum from the planar mode down here up to the thickness up here. And then you see all the different, there's some different modes here compared to what Erling showed, because this geometry is more complex than just a thin disk. Just see here.
Nikolaj, you have a question?
Yeah.
Did you define any boundaries?
Actually, not for this model. I didn't really. In the solid mechanics, it's just free boundaries, so it can vibrate as it wants. So it's similar to when you measure with your impedance analyzer, just holding it with the tweezer in air.
Okay.
But when we start doing the coupling to water and stuff, we will have to put on a few boundary conditions. Okay. So what we would then normally do with the simulations, if we have the spectrum, we want to look into the resonance we are interested in. So now we know it will be around this thickness mode, but if we had a lot of coupling modes between planar and thickness, we could try to look in at different ones and see which one actually vibrated in the direction we wanted. So if we check this resonance down here, it's around 1050, 70 kilohertz, right? So what we can then do is go in and look, how does this vibration then look? So we plot it here. So this then shows color scale is the displacement of a particular region of the piezo, and then there's some deformation, hugely exaggerated how much it deforms. Obviously, it will be nanometers in reality, but it gives you some idea of how the vibration looks. And we can, what I would typically do to quantify which kind of mode it is, I would do an animation, because then you can see how it actually fluctuates. So you see this is a nice thickness mode. You have piezo moving, expanding and contracting, and then you have some corner effects where it wobbles a bit or a lot. Because one thing to keep in mind is that when we just do a plot, you will only have one time point in your whole oscillation, and it might not be the maximum displacement. It's just some random point in it. So often you have to actually go in and do the animation to really look at how the mode looks. Then we had to check the mesh, if that's fine enough. So I'll add a mesh, and then I will move the deformation, and then we plot it again. Then you can see here how well resolved we have. So the high points and the low points, and you see we have quite a fair amount of mesh elements between the different high nodes. So this will look fine from a mesh point of view. If, on the other hand, to go back to the impedance spectrum, if we were looking to drive our transducer at the third harmonic of the thickness mode, so up here at around 3 megahertz or 3.3 megahertz, if you start to look at this, so 3.35, I think, here you see, due to the higher frequency, the wavelengths are much shorter, and then our mesh doesn't at all accurately resolve the features, right? There's only 1 or 2 elements between each high and low point. So if we were looking to drive our transducer at this frequency, we would have to put on a finer mesh to get some accurate result from the simulation. Yeah, so then the coordinate system I mentioned. So I said that we could define which coordinate system to use for a material, and that the material properties were linked to the polling direction. But obviously the software doesn't know which direction the polling is, so that's what we define with the coordinate system. And what I show you here is just the simple XY coordinate system. So for this, the material would assume it had been pulled along just the Z direction. And obviously this wouldn't provide like accurate result, no matter how well you have set up all the mesh and your boundaries. So what you could do instead is you could, for this circular shape, you could define a circular system. So this is defined from sine and cosine of the angle and the radius, right? And you see it follows much more nicely. You have the Z direction along the polling between the two surfaces. So this is much better, but it doesn't really cover the corners up here, because up here it would not be pulled like this, because the field line will go from this electrode up to the top electrode, something like this. So to get the most proper one, you can do, at least in COMSOL, you can do this kind of simulated ones where you see how it follows this shape and then terminates at the surface. And this will obviously increase the accuracy of your model. How much it matters depends on, you know, how big a volume your edge or your corner is compared to the entire model. Yes, so I think that was it for the freestanding one. Then we will look at the coupling to water. See if I have the view here. So this is the model you have. In the bottom, you have the piezo, the hypertransducer, and then we have added a big sphere of water up here, and this shows the intensity, the focusing of the acoustic energy here in the center. So in the cross section, it looks like this. We have the piezo like before on the bottom, then a big sphere of water. And then we have this layer on the outside, which is an absorbing layer, because if you don't put an absorbing layer, you will have a standing resonator where all the waves traveling from the transducer through the water, they will then be perfectly reflected at the boundary and then go back, and you'll have some standing wave system, which doesn't at all compare to what you would probably have in reality. So by having an absorbing layer, you can simulate that all the energy just dissipates like it would in a water tank or in the body. Let's see. So in the material, we still have the piezo, and then we have just water for the other ones. So for water, you will define some acoustic properties, which is needed. Then, so the solid mechanics would be the same, because these physics are only applied in the piezo domain. Same for the electrostatics. Then we have, so then you will have different physics, pressure acoustics, governing all the other areas. And then you have this perfectly matched layer. So that's what this absorbing boundary is called. That's when you do simulations in frequency domain. You have perfectly matched layers, which kind of like stretch the domain into infinity through some equations, and then they can dissipate all the energy. And the perfectly matched means that the acoustic impedance of this layer matches perfectly with the water, so you won't have any reflection on the boundary going into the layer. But otherwise, actually, we didn't set any special boundary conditions or physics for the acoustics. Then for the coupling between the mechanical to the acoustic domain, this then just this boundary where all the mechanical vibrations will then generate pressure in the water. That's how those two link together. Then for the mesh, obviously we have the piezo the same. Then for the water, we also need to resolve this. And as you see, the mesh elements are actually smaller, and that's because I also define these based on the wavelength in the water, and because the wave speed is slow in water, you get shorter wavelengths, so you need finer mesh elements. And then for the perfectly matched layers, it's preferable to have these square elements, because then they can stretch along the traveling direction and then absorb all the energy. Okay, so then we can look at the results. So let's see the impedance spectrum. Yeah, okay. So then we do the simulation at all the different frequencies, and we plot the impedance spectrum based on this. And so the blue is the one I showed before, just the freestanding one. Then we put in the water. We see that what it mainly does is that it simply dampens all the resonances. So if we zoom in here on the thickness mode we're interested in, we can see the green one is much lower impedance value, which means less vibration and lower intensity. And then you will notice I put the Q value up here, and that's because I defined the Q value for the simulation, and the water itself, the coupling from the water, doesn't dampen the piezo as much as it does in reality. So what you would often always need to do is compare your model with an experiment, and then include a quality factor that matches your real experimental setup. So here I did a sweep with 4 different Q factors. Let's just plot it. And I'll zoom in again. So here you see how Q factor from 10 to 100 of our piezo in water. And you see, I should just zoom in on the in water ones. Oops. You see how lower Q factor, more damping, you have less clear resonances. And what I always do is look at my measured impedance spectrum, see how sharp the peak is, and then apply a Q factor best fitting the measured value. Yes, so then that was the damping. Then we want to look at the acoustic field, because now we have all the coupling into water. So this is how it looks. I put the frequency of the planar mode. So we see the vibration of the piezo down here as before, and then we have the pressure field going towards the center, where then it's focused. So we have very high pressures, and then it exits again. And I will just, similar to before, I think we should show an animation to best see how it actually looks. So here we have clear thickness mode, and every time you have an expansion, you get a positive pressure, and the contraction gives you a negative pressure.
Nikolaj, you have a question here from Matthew.
Yeah.
Did you add some attenuation coefficient for water?
So actually, no, I didn't add attenuation for water. So that's kind of lacking in this model. But yeah, similar to the damping for your the piezo, you have to consider damping for all the parts in your model. Actually, that's very rarely included as standard in modeling. Yeah. So what I would then, so if I continue, so I would then use this animation to not only just look at how the wave propagate, but also to evaluate if my absorbing layer actually works correctly. Because we see the waves propagating towards the center, as they should, and then they continue to the sphere, and then we can look at, so now you see when they reach the boundary to the matching layer, they travel into this layer, and then they kind of like just disappear. It dissipates. So this seems to work really nicely. If you have set out a wrong matching layer, you might see some waves being reflected and going back into your model, and then we'll show you something is wrong. Especially if you go down here where you have waves not going into the layer perpendicularly, but kind of like at a big angle, then it's more difficult to absorb these waves. But they also seem to dissipate nicely, not being reflected up. So this kind of shows you that the model seems accurate. Then what you typically will look at is not the pressures, but the intensity. So if you look at this, you can then see how you have the focused intensity in the center, and you can start looking at how it changes with the frequency and such. And there's some analytical scaling laws for this, which this was also presented in one of our earlier webinars on high frequency transducers. What we could then also look at is some line plot. So I want to show you, if we take a point plot here, take a point exactly in the center, and then take the acoustic intensity of this point versus your frequency, then we can compare this to the impedance spectrum. This is what you see here. Green intensity, nothing for all the low frequency planar mode, but then when we have the thickness mode, we see a peak, and then also for the third harmonic, a very tall peak. Because this could lead you to think that, oh, we need to drive at a third harmonic, but there's other factors you need to consider that's not included in the model, and the model will only be as accurate as your material parameters and also all the other things you set up. And so, for example, it doesn't include anything with your electrical driving system, how effective this is at different frequencies or at different impedance levels, and also the heating and losses will be different from the resonance to the third harmonic. So there's all kinds of factors you need to adjust for. And also, the only good way to really compare these is to have to actually do some experiments. We don't have good enough material data to just do the complete simulations and then you know how to build your device. And also, if we zoom in on just the thickness mode, you will see that at here, low impedance at the resonance, we have the highest intensity, the acoustic intensity. But actually, in reality, you often drive the transducer at the anti-resonance, because here generally have lower losses and in the piezo. And this is also not really captured in the model because we don't have all this driving system features included. But what you could kind of use this kind of model for is to look at how much frequency variation you can tolerate with in respect to intensity variation. So if you look at, for example, 50% drop in your intensity, how much frequency variation would this corresponds to? Then you know if you can just live at a fixed frequency of your driving system, or if you need to have some tuning available to always hit the maximum. Okay, so then just really quick, I see the last model with the holder. So what we just defined is I put a big block down here, glue it. Obviously, you would normally want air backing, but this was easier to draw and it shows some nice properties. So I defined some material for the holder, just some common plastic material, and I put the Young's modulus so that I can vary this and see how different materials will affect my model. And then a good tip is for the glue layer, you don't have to model it as a physical thick layer. You can just do it as a boundary where you define some material properties. And then you can also define it as just an elastic layer, so similar to a thin mechanical layer with some simulated thickness, and also still have the damping involved. Then you don't need as many mesh elements, which is particularly important for 3D models. Otherwise, all the setup is the same. And we can then start looking into here. How would your holder affect your transducer. So if you have, now I have the frequency of the thickness mode, and we have a very stiff holder, you see a lot of vibration going on in the holder, while if you have a softer material, most of the vibrations will only be very close to the piezo, and then they will dampen and die out. So this can show you give you some input on which kind of material you should choose for your holder, and also how large a bonding region you can actually tolerate without affecting your intensity or your piezo vibration too much. Okay. Oh, lastly, so this was the model I want to show you. Then one last thing to show is how else to use simulation in your organization, because obviously setting up this kind of full model requires a lot of engineering time, and it's very complex. You need a lot of training in it. What we have also done to use simulation in a wider part of the organization is to have make this GUI for an actual COMSOL simulation. So behind this, you have all the same settings I showed you, but then this is particularly designed for the sales team, so you can choose different shapes. You see this HIFU lens I just had. Define your dimension, and you can run full simulation. So this can be used, particularly useful if you have geometries where thickness and planar dimensions are very close to each other. Then you can quickly evaluate the customer response and see where you have the resonances and which kind of dimensions to choose to hit the right frequencies you want. So this can, and they can also share these kind of simulations with you whenever you come with a request for a quote. Okay, that was all for me. Louise, you want to continue?
Yes, so thank you very much, Erling and Nikolaj, for a very good presentation. Now there's a time for questions. If anybody has more questions on their mind for both Erling and Nikolaj. If just to give you just a little chance to type if you have one question, Erling, I was thinking, could you explain a bit more what the practical difference is between, the normal loss and Q and the complex losses, the practical difference between those?
Yes. Nikolaj also mentioned a little bit that having just, for example, one QM factor means that you assume just isotropic losses. One number describes all, but if you are actually able to determine complex coefficients, then you can actually distinguish between, for example, mechanical losses in the 3-3 direction and those mechanical losses relevant to shear, which would be in the 5-5 direction. And so you can really go into details and get a more precise determination of how the losses affect your material. And of course, it's quite a bit more difficult because how to find these complex parameters. And I mentioned that we are using this Spanish program, but we are just in the process of getting basically complex data sets for more of our materials. At present, we can, for example, supply it for PZ27, but we don't have it for all materials. Okay.
Thank you. Okay, so there's coming a bit more question in here. First is from Kaiser Contreras. For Nikolaj, do you have any recommendations for learning COMSOL for piezos?
I think for learning the COMSOL particularly, they have a lot of webinars you can actually use. Both on the homepage of webinars, you can watch for free, and a blog post. And they also, if you have the COMSOL software, they have a lot of good application models where they have built some model, and you can go in and they describe how it's been set up, and you can use those as templates for building your own model.
Okay, thank you. So the next one's coming in here is from Abdulgafar Basega. I have a question about new piezoelectric materials development. Is there any new one that Ferroperm is working on?
Yeah, maybe I can answer that. So nice to see you again, Gaffa. It's been some time. Any new material we're working on? Yes, we are certainly working on lead-free materials here at Ferroperm, because we need to be able to provide and supply materials that are not PZT for the future, where the ROS regulations may be put into place. So we are working on a few different lead-free materials, both based on KNN and on the NBT BT.
He's also adding that he's interested in textured ceramics.
Yes, and I can add that mainly our colleagues within CTS actually have a textured material which is based on a lead-containing composition and showing quite good properties, and also working on a textured lead-free ceramic. So please feel free to contact us, and we will refer to people working exactly with those. Yeah.
Yeah, thank you. And we have a question from Anil. What is the dimensional ratio for different shapes like rod, plate?
Yes, I can take that one as well. So for the rod that I showed, a normal recommendation is at least an aspect ratio of 3:1 and better 5:1. But I would say it really depends on your material, because in some cases maybe 2.5:1 would be enough. But if you look at the resonance and see that it's not really pure, then you maybe need to go all the way to, for example, 5:1. And for the thin plate or thin disc, we would recommend at least 1:10. So 10 times the thickness for the diameter, and often it would be better to have 1:15 or 1:20.
Thank you. And then we have from Nikolaj Feidenhans'l. Hi, Erling, could you tell more about frequency-dependent properties? Which material properties can depend on frequency?
Yes, I would say the simplest example is actually the permittivity. It's clear that if you go from a very low frequency like 1 kilohertz and to a very high frequency like 10 megahertz, you'll really have the what we call the free and the clamped permittivity. But even for some materials, you'll have some variation even before you hit the first resonance, and this is the case. It's more pronounced for certain materials than for others. I didn't have time to go into details, but we saw for this KNN material that the frequency dependence was larger than for example, a soft PZT. So it's something you need to look into in more detail. Maybe for some people, it's even more serious that the things like the D33 coefficient will also be frequency dependent. So if you measure with a D33 meter at maybe 110 hertz and compare that with what your impedance-based characterization will give you at 200 kilohertz or 1 megahertz, those numbers will also not be quite the same. But I would say that one would actually need to look at the specific material to see how different it looks. But we are at least getting more insight into that to learn more about the frequency dependence.
Yes, yeah, so I think we have to also stop now. So we can maybe get back to you, Neil, on your follow-up question. But thank you very much, everybody, for your questions. And we would kindly ask you to fill in our survey at the end. And then we would like to share the remaining program. So we'll hope you will join us again later on on some of our next webinars. So thank you very much for joining us today, and we look forward to conversations in the future. Thank you.